Hello, mathematicians. Let's talk about the logic of compound statements, beginning with conditional statements. So, conditional statements are statements of the form if P, then Q. And so, P and Q are statement variables. The conditional of Q by P is if P, then Q. Or we might say P implies Q. And we can write that shorthand with an arrow from P to Q, meaning if P happens, then Q is sure to happen as well. The only time that this conditional statement is false is when P is true and Q is false. Otherwise, P implies Q is true. P is called the hypothesis, also called the antecedent of the conditional, and Q is the conclusion or consequence. Now, I want to emphasize this again, the sentence that says it is only false if P is true and Q is false. Otherwise, it is true. If P is false, it doesn't matter if Q is true or false. The statement is true. Because the only way it can be a false statement is if we can show that P is true and Q is false. So be careful with that. Now, a conditional statement that is true by virtue of the fact that its hypothesis is false is often called vacuously true or true by default. So consider this statement. If 0 equals 1, then 1 equals 2. As strange as it may seem, since the hypothesis of this statement is false, then this statement as a whole is a true statement. Because remember, the only way it could be false is if this part is true and then the second part is false. In expressions that include an arrow as well as other logical operators such as and, or not, the order of operations is that the arrow, the implication, is performed last. So it says construct a truth table for the statement of the form P or not Q implies not P. So, let's see, do we have a truth table? Good. So by order of operations given, the following two expressions are equivalent. So we're going to start by doing P and not Q and not P, and we'll see if this implication holds. So let's take a look at the truth table. So we begin, just as we've done in the past, with our first two columns being all the possible combinations of P and Q. So remember, either P and Q are both true, P is true, Q is false, P is false, Q is true, or they're both false. So those are all the combinations of P and Q that we could have. Now notice that our statement that we're looking at contains not P and not Q, and so we need columns for both of those as well. And those are very easy to construct. If you take all of the values in the first column and just switch them, you'll have the not P column. And if you take all the values in the second column and switch them, you will have all of the values in the not Q column. For the next column, we have P or not Q. So we are looking at the first column and this column here, the not Q column. So this is, remember that the upside down or the V stands for or. So in order for this to be true, we just need either P is true or not Q is true. So we'll be looking here. P is true in the first row. Q is false. So we only need one of them to be true. In the second row, P is true. and not Q is true. So certainly at least one of them is true. In the next row, P is false and not Q is false. So that's the only way that the or statement can be false. And in the last row, P is false, not Q is true. So since one or the other is true, the or statement is true. Now, here's what you're going to do for this last column. You're going to be looking at the hypothesis, which is P or not Q, and the conclusion, which is not P. So that comes from here's the hypothesis, here's the conclusion. All right. Remember, the only way that's going to be false is if the hypothesis is true and the conclusion is false. So look at these first two rows. The hypothesis is true and the conclusion is false. So that's why we have a false here and here. Otherwise, it is true. Okay. So, whoops, sorry, I forgot this one. This one has a truth value as well, but the conclusion is also true. All right. If the hypothesis is false, remember, then we say it is vacuously true. It doesn't even matter that the conclusion is true. I hope that made sense. All right, let's talk about logical equivalence involving the implication arrow. All right, this is about division into cases, which is sometimes necessary. We're going to show that P or Q implies R is equivalent to P implies R and Q implies R. So again, we are going to use a truth table to hash this out. Since we have 3 statements, then we need an 8-row start for P, Q, and R. So we begin with these first 3 columns, all the possibilities of P, Q, and R, ranging from they're all true to they're all false and every combination in between. All right, moving on to the P or Q column, we simply look at P and Q and see if at least one of them is true. And the only place that at least one of them is not true is these last 2 rows where P and Q are both false. So you see those false readings here. All right, when we look at the P implies R, again, the only time this could be false is if P is true and R is false. So find the cases where P is true and R is false. I see here P is true and R is false. So we're going to have a false here. And then here P is true and R is false. So we have a false. And that's it. That's the only time P implies R can be false. The rest of the time it's true. Even when P is false, we cannot make an assumption. We just say the statement is true. All right, we do the same thing for Q implies R. Only we're looking at the Q and R columns. Again, the only time Q implies R is false is when Q is true and R is false. All right, so in this column here, it says P or Q implies R. So we're looking at P or Q column, and we're looking at the R column. Again, the only time that that statement is going to be false is if P or Q is true and R is false. Okay, that happens here and here and here. And so those are the places where P or Q implies R is false. All right, finally, we're looking at the, let me just kind of use a different color here. So here we're looking at the P implies R column. We're looking at the Q implies R column. And the symbol in between stands for and. So it's only true when both of these are true. So in the first row, true, true, so true. In the second one, false, false, so false. Third, true, true, true. False, true, false. Because remember, they both have to be true for an and. True, true, true. True, false, false. True, true, and true, true makes true, true. All right, so to determine if these two statements are logically equivalent, compare each of these rows line by line. Okay? Are these the same? Yes. 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 And yes. Because the truth values are the same for every single row, then we can say that these two statements, this one and this one, are logically equivalent. Okay, so let's rewrite the following statement in if-then form. It says either you get to work on time or you are fired. There's no if and there's also no then in this statement. So how do we turn it into an if-then statement? Either you get to work on time or you are fired. Okay, so not P would be you get to work on time. Q would be you are fired. So the given statement is not P or Q. Okay, so P is you don't get to work on time. So in the if-then version, P implies Q is if you do not get to work on time, then you are fired. And so the purpose of that little exercise is if you have a statement and it's not in if-then form, in order to proceed with logic, it's often helpful to reframe your sentence, reword it in an if-then form, and so that it's a P implies Q situation. And that is sometimes harder than it seems. Now let's talk about the negation of a conditional statement. So by definition, P implies Q is false. Remember, if and only if its hypothesis P is true and its conclusion is false. So it follows that the negation of an if P then Q is logically equivalent to P happens and Q does not happen. Okay? So we can say it like this, P and not Q. All right, so that's how you can take a conditional statement and negate it. To negate something is to change its truth value. So if P implies Q is true, then the only way for that to be false is if P is true and Q is false. Okay, so P and not Q. Okay, and so it says to obtain this result, you can also start from the logical equivalence. P implies Q, and you can negate it is equivalent to not P or Q, and you can get there as well using De Morgan's law. All right, so let's think about that. Let's practice that. It says write negations for each of the following statements. If my car is in the repair shop, then I cannot get to class. So remember, how is this going to be negated? Okay. My car is in the repair shop and I can get to class. So you keep the P part and then you not Q it. All right, let's look at the second part. If Sarah lives in Athens, then she lives in Greece. So to negate this, we would say this part and not this part. So Sarah lives in Athens and she does not live in Greece. Okay. We happen to have an Athens, Texas. So perhaps Sarah lives in Athens, Texas. All right, let's talk about the contrapositive. So, one of the most fundamental laws of logic is the equivalence between a conditional statement and its contrapositive. Okay. So, if you have if P, then Q, it is logically equivalent to if not Q, then not P. So, if you have a conditional statement and you switch the hypothesis and conclusion and also negate them, you will have a logically equivalent statement called the contrapositive. Okay. So the contrapositive of P implies Q is not Q implies not P. All right. Another restatement of that. A conditional statement is always logically equivalent to its contrapositive. So let's practice writing a contrapositive from an if then statement. So if Howard can swim across the lake, then Howard can swim to the island. So Howard can swim across the lake is the hypothesis. Howard can swim to the island is the conclusion. We're going to switch those and negate them. Howard cannot swim to the island. If Howard cannot swim to the island, then Howard cannot swim across the lake. Okay, and you see that here. All right, part B says if today is Easter, then tomorrow is Monday. So we're going to take the hypothesis and conclusion. We're going to leave if and then where they are. We're not moving if and then. We're only moving the clauses P and Q. And we're also going to negate them. So it would say if tomorrow is not Monday, then today is not Easter. Okay, we have some other variations of conditional statements that we should talk about. One is the converse and one is the inverse. So if you have a conditional statement, if P, then Q, then the converse is if Q, then P, where you simply switch P and Q. The inverse is where you don't switch P and Q, but you negate them. So the converse of P implies Q is Q implies P. And the inverse of P implies Q is not P implies not Q. Now, it should be noted that the converse and the inverse of a conditional statement are not logically equivalent to the original conditional statement. Okay, certainly not always. Please excuse my barking dog. So let's write the converse and inverse of each of the following. So we have our statement, if Howard can swim across the lake, then Howard can swim to the island. So we have, go back to my pen here. So Howard can swim across the lake is P, and Howard can swim to the island is Q. So for the converse, I'm just going to switch those. I'm going to say, if Howard can swim to the island, then Howard can swim across the lake. Okay, so that would be P implies Q. So that would be this one, just switching P and Q. All right, the inverse, I'm going to keep them in this same order. I'm just going to negate them. If Howard cannot swim across the lake, then Howard cannot swim to the island. We have that here. So notice the converse is switching P and Q. The inverse is negating P and Q. And the contrapositive, which we talked about previously, is a combination of the converse and inverse, where you switch P and Q and negate them. All right, let's try. If today is Easter, then tomorrow is Monday. So for the converse, we simply switch the two clauses. If tomorrow is Monday, then today is Easter. And for the inverse, we leave the P and Q right where they are. We simply negate both clauses. So if today is not Easter, then tomorrow is not Monday. So I encourage you to take a moment, go back and take a look at that and make sure that you can process that, because you certainly should be able to write any of these variations. Given any conditional statement in if then form, you should be able to tell me what is the converse, what is the inverse, and what is the contrapositive. So again, a conditional statement and its converse are not logically equivalent. A conditional statement and its inverse are not logically equivalent. If you know this and you start watching ads or advertisements or maybe listening to the news or politicians, you will find that these fallacies are often stated as fact. So someone will state a converse as being logically equivalent, when in fact that is not the case. Now, the third point is interesting. The converse and inverse of a conditional statement are logically equivalent to each other. So remember, if you have P implies Q, the converse is Q implies P. The inverse is not P implies not Q. Notice that these two statements are simply contrapositives of each other, and that's why they are logically equivalent. All right, if and only if, and the biconditional if and only if. Okay, so these can be really, really tricky. Language in logic is super important, so pay special attention to these little words and, or, only if, and if and only if. So P and Q are statements. And if you see something that says P only if Q, it means if not Q, then not P. Or equivalently, if P, then Q. So you really have to kind of think about that with an example for that to really process. 'Cause that might not seem logical until you use a specific example. So here it says, John will break the world's record for the mile run only if, so here's that, only if he runs the mile in under 4 minutes. So think about that. John will break the world's record for the mile run only if he runs the mile in under 4 minutes. Only if, no other way. Okay? So how can we say that? If John does not run the mile in under 4 minutes, then he will not break the world's record. Or if John breaks the world's record, then he will have run the mile in under 4 minutes. Again, I really encourage you to go back, take a minute to process this, think through this example with John, make sure that makes sense to you. Maybe make up your own example, because that can be tricky. Okay, so we've talked about only if. Now we're going to talk about the biconditional if and only if. Now, this is called a biconditional because the statement is true forward and backward. In other words, the statement, it's a way of saying that the statement is true and its converse is also true. Okay? And so we use the words if and only if, or sometimes we really get lazy and just say IFF, if and only if. So here is the truth table. So the truth table is that when in the biconditional, the statement is true only when P and Q have the same truth value. Interesting. In order of operations, you can treat the double arrow the same as a regular forward-facing arrow. As with and or, the only way to indicate precedence between them is to use parentheses. So here's the hierarchy of order of operations for the logical operators that we've used so far. So first, evaluate any negations. Then evaluate any ands and ors. Finally, apply the arrows. All right, here's another example. Here's an if and only if example. It says, rewrite the following statement as a conjunction of two if then statements. Okay, so it says this computer program is correct if and only if it produces correct answers for all possible sets of input data. Okay, so this computer program is correct. That's your P. It produces correct answers for all possible sets of input data. That's your Q. And in the middle, you have this if and only if, separating it. It simply means that P implies Q and also Q implies P. All right, P double arrow Q. So that's what if and only if means. Okay, so we could say it forward. If this program is correct, then it produces the correct answers for all possible sets of input data, and we could turn it around. If this program produces the correct answers for all possible sets of input data, then it is correct. It's called a biconditional. Okay, these are fun too. Necessary and sufficient conditions. Okay, so think about what these words mean. Necessary means it can happen no other way. Sufficient means it's enough, but other things could also happen. Okay. All right. So if it says R is a sufficient condition for S, this means if R happens, then S will happen. But that it means that R is not the only way for S to happen. Okay. That's what a sufficient condition means. Okay. If R is sufficient for S, then R is merely one way to ensure that S happens. But maybe something else could also make S happen. A necessary condition means S won't happen any other way besides R. So if not R, then not S. Okay? So you will see these words, a necessary and sufficient condition. So the words mean different things, so be very careful with them. So let's rewrite the following statement in the form if A, then B. So Pia's birth on the U.S. soil is a sufficient condition for her to be a U.S. citizen. Okay. So a sufficient condition. What that is saying is, since if Pia is born on U.S. soil, that is one way to be a U.S. citizen. It is not the only way. So we can simply say, if Pia was born on U.S. soil, then she is a U.S. citizen. Okay. Use the contrapositive to rewrite the following statement in two ways. George's attaining age 35 is a necessary condition for his being president of the United States. This means there's no other way. If George does not attain the age of 35, there is no way for him to be president of the United States. There's two ways we can say this. If George has not attained the age of 35, then he cannot be president. And if George can be president of the United States, then he has attained the age of 35. So again, if we go back here, George attaining the age of 35 is P. His being president is Q. And so this says not P implies not Q. And this says Q implies P. Once again, I think some of these things require you to slow down, rewind this video, let yourself process this, make a note of it, because yes, it is logical, but it can be very, very tricky.